maestro en ciencias computacionales, también por el Tecnológico, con estancias de investigación en la Harvard Medical School y, felizmente para un servidor, estudiante de doctorado bajo mi supervisión en ciencias computacionales. El título de la plática de Leonardo es Finding Optimal Solutions to MaxSAT Using a Quantum Computer. Y sin más, Leonardo, bienvenido, gracias por estar aquí y te cedo la palabra. Tienes 11 minutos con todo y preguntas y respuestas.
Ok, gracias. Voy a tratar de ser súper breve. Entonces, good morning, everyone. Good afternoon, everyone. My name is Leonardo Clemente, and I will be showing you a little bit of what I've been working on during my PhD in this presentation. I am mainly focused in the development of quantum algorithms to solve satisfiability problems. So the key takeaway MaxSAT into a quantum computer and then combining this encoding scheme with quantum phase estimation and amplitude amplification to find such solutions. Now I'm going to begin really quick by defining three key concepts for the algorithm. One of them is what is a Boolean expression, second is what is a truth assignment, and third, a function n, which is deeply associated to this function f, the instances of MaxSAT. And then I'm going to jump directly into the algorithm. Now, to go really quick, a Boolean expression.
Sorry, Leonardo, would you mind speaking a bit louder?
Yes, can you hear me now? Can you hear me better? Okay, yeah, so I'm gonna show what so what is a Boolean expression? A Boolean expression is basically a function, and this function is comprised of three things. So the first thing is a number of variables, which is denoted by the letter n, the number of clauses, which is denoted by the letter m, and then a third variable, which is the letter k, which is not the number of variables within such clause. In this example, then we can just see that I put this example just to show you a description. An actual description. So for this function, we have an n equal 3, so 3 variables, m equal 2 clauses, and k equal 2, so 2 variables within the clauses. The clauses are basically the groups within the parentheses. Now, after defining this, I'm just going to define what a truth assignment is, and this is very important. I know it's really simple, but it's very important to explain the algorithm correctly. So a truth assignment is just basically assigning the values, assigning a set of values to the Boolean variables. And here I have two examples. The first one on the left is the truth assignment of 0, 0, 0 to these variables C3, C2, and C1. And on the right side, I have an example of a truth assignment, the truth assignment 1, 0, 1 to these variables. Now, I'm also showing the evaluation of these truth assignments for f of c, right? And because I want to so this function and information about the number of clauses that, after evaluating such function, collapse into either 0 or 1 within the clause. So in this case, the function n of the truth assignment 0, 0, 0 would be 1, because in this example, we only have one clause that turned into 0, right? And then on the other example, n would be 0 because we have no 0 clause. To recap really quick, f of c is just a function defined by 3, the number of variables, n clauses, and k is the number of variables within the clauses, right? Phi is just the action of assigning a set of values to these variables, and n is a function that tells you the number of clauses that turn into 0 after evaluating f of c under such truth assignment phi, right? Now, after defining these, I'm just gonna tell you what the MaxSAT problem is about. So MaxSAT is basically answering this question. Given an instance of MaxSAT f of c, so this Boolean expression, what is the minimum value that n can take, right? So this also means what is the maximum number of classes that turn into 1, right? Equivalently, this means what is the minimum number of classes that turn into 0. This problem is very hard for people who know. This is an NP complete problem, and that's why I am working on this during my PhD thesis. Now, I'm going to jump into the algorithm because I don't have that much time. And so I'm going to begin by answering this question. How do we encode this function f of c into a quantum computer? The answer to this is there are many ways to do it, and it's still an open question. But I'm going to show you how I do it and why I do it to solve MaxSAT, this question for MaxSAT, right? Now, I'm going to start with this function f of c, an arbitrary function f of c, and the main objective of this encoding is to turn this function into an unitary operator, which is diagonal. So this means that the eigenvalues are in the diagonal of such operator. And the important thing represents and encodes this instance f of c is that each of the eigenvalues within that operator have information about this function n, which I told you is really important, right? Now, if we assign to the computational basis states of a quantum computer if we assign these computational basis states to different truth assignments, as down below here, we can see that if we operate we operate f into such a basis state that is associated to a truth assignment, we would then get the same basis state plus the eigenvalue, right, which is just a phase shift. And this phase shift encodes the information of n evaluated under such truth assignment, right? Now, how do we build this f operator which encodes that function? This is pretty simple. We break down this operator into a product of sub-operators, which I denote by the letter G here. So the key takeaway on this deconstruction is that each sub-operator G is associated directly into a clause, right? And here I'm going to show you with an example because I think it's the easiest thing to do. If we have a clause, I want to say also that these operators G are associated to control C rotations in a circuit, right? So in this example, to encode this Boolean expression, we use two control C rotations because we have two clauses. And I'm just showing this very quickly. And now I'm going to skip this for the sake of time to keep questions open. And what I want to say is that we use this encoding we use this encoding and combine it with quantum phase estimation and amplitude amplification. Right now, just one last thing on the encoding is that this encoding is constructed in linear time in a quantum circuit, and that's why it is very useful. Now I'm going to jump to the next steps of the algorithm. After we have created this quantum circuit, we use this f operator and combine it with quantum phase estimations to encode f of c and also sort, do some kind of sorting over the possible solutions of our problem. And after we have sorted these and grouped up these solutions, we boost the probability of finding the solutions that we're interested of using amplitude amplification, right? Now, I'm gonna go really quick on this second step, right? This second step of using quantum phase estimation, I'm not gonna go over the circuit, but what I really process of combining quantum phase and the operator all the solutions into states which with the it groups all the solutions into different groups, and what the groups have in common is the output of the function n. So if we see this graphically, this would mean that after applying QPE, we would get we would get this distribution if we sample the quantum computer, and we would see sorry, I tried to go over really quick, and I'm trying to mess up. So I want to take a few seconds. What I wanted to say is that this application of quantum phase estimation, what it does is that it groups up all the possible truth assignments which are associated to basis states, and it groups them up in a distribution that looks like this. And after doing that, we use amplitude amplification to boost these solutions that we're interested in. So if we go back, the solutions that we are interested in are the ones on the leftmost side. And yeah, so I'm out of time, so I'm really sorry about that. I thought I would have a little bit more time, so I don't know. We have to cut here, Salvador, right?
Yeah, that's okay. Thank you very much. It was a great introduction to the topic, I have to say,
Yeah.
particularly given, the time constraints. So there is
Yeah.
chance for, I think there are no questions. No, there are not. So I think we should stop now and go to the next talk. Thank you very much again for being here, and see you
Yeah.
soon.
Yeah. Thank you, and I apologize for the time constraint. Yeah.
That's all right. Cheers. Thank you very much.